Oh no, the Death Eaters have destroyed Hogwarts and our magic wands are all broken from that epic battle.
Yeah, we'll need to put the giant bricks together using our own hands.
Well, why don't we use hydraulics and levers?
How do we do that?
Don't you know about muggle physics?
No.
Well, let me explain it to you then.
Wait, where did that board come from?
A lever consists of a rigid bar that can rotate around a fixed point called a fulcrum. When a load is placed at one point, a force applied to the different location can move the load.
That's the bee's knees, Hermione. But seriously, that board was not there 2 minutes ago.
There's more. There are 3 different types of levers. The first class lever is one in which the fulcrum is somewhere between the load and the applied force.
Just like the seesaw. Whee!
Stop it, Ronald. You're embarrassing me. You too, Harry. Now, a second class lever is one that has the load between the fulcrum and the applied force. Can you guess what the third type is called?
I know, a third class lever.
That's right, Ronald. A third class lever is one that has the force between the fulcrum and the load.
Ooh, tell us more.
The turning effect of a force on a lever is called torque. When there is more than one torque applied to a lever, the lever will balance if the sum of the clockwise torques is equal to the sum of the counterclockwise torques. This is called the law of the lever. This can be expressed in the equation T is equal to F times L.
But Hermione, how is this going to help us rebuild Hogwarts?
Just look.
Wow, how does that work?
Oh, I know. That machine uses a first-class lever, which multiplies the effort that was applied and makes our job easier.
No, Harry, you've got it all wrong. Look, the lever arm from the syringe to the fulcrum is shorter than the lever arm from the fulcrum to the teeth where the load is. That means the hydraulics must exert a strong force. But the small, slow motion of the hydraulics will become a large, fast motion of the teeth holding the load. This is good, since hydraulics produce huge forces, but do so slowly and for short distances.
Wow, Hermione, that's amazing. Tell us more about this hydraulic machine.
Okay, there's another lever. The syringe in the middle lifts up the great arm of our excavator. The great arm is essentially a third-class lever. The force from the hydraulics where the syringe attaches to the lever is in between the fulcrum and the load. This force will be greater than the force at the end of the lever arm, but that is okay because hydraulics produce great forces slowly, for short distances, and the end of the lever arm will move faster at a greater distance.
Well, what about all these hydraulics? How does that work?
Hydraulics follow Pascal's law, which can be derived from pressure in is equal to pressure out. And since pressure is force divided by area, we can show that the force out over the force in is equal to the area of the cylinder out over the area of the cylinder in.
Well, these syringes are all the same size.
Yes, I know. The hydraulics door was out of small syringes. Just imagine that the syringe that you are pushing is a tiny syringe. Since its area is smaller than the syringe that is on the lever arm, according to Pascal's law, the force on the syringe on the lever is multiplied by the amount of times its area is larger than the syringe I am pushing on. However, this syringe moves less than the one I am pushing, so work and energy are all conserved.
Great! Let's all get to work!